Good morning, good afternoon, and good evening. I'm pretty sure some of the attendees are joining from different part of the world. Well, it's a different time zone. So welcome to today's webinar organized by Geofabrics Academy in partnership with TenCate Geosynthetics. Today's webinar topic is Basal reinforcement embankments on soft foundations, part 1. And if you are not aware, the part 2 will be already confirmed for the next Wednesday, same time at 1 p.m. So if you haven't registered for that particular webinar too. Now, what I would like to do is, my name is Rajesh Basal. I'm working as a National Business Development Manager, Infrastructure for Geofabrics webinar. So just give you some housekeeping. You all are muted, but at the just for the easiness purposes, so that a presenter can present it properly. Some housekeeping. Other thing is, you can see a Q&A button at the base of this Zoom meeting. If you have any questions, please don't hesitate to type in that questions. And at the end of this presentation, Chris will try to answer as much as question possible. The other thing is, if we can't answer all the question, we will try to get back to you by emails or other options. I'll just give you a heads up on other things too, that this webinar is also recorded. So that will be uploaded within 24 hours on our website. Now, let me give you some overview for this particular course for the part 1. So today, Chris will be providing a good understanding into the design of the embankment over the soft ground. And he will also provide some very good understanding on what to be considered when you consider or when you use high-strength geotextiles, and what performance you are targeting to meet your road authorities requirements. Now, let me introduce Chris first. I think so you may attended some of the previous talks in Australia, organized by Geofabrics. Chris is a well-renowned and knowledgeable guy, a knowledgeable person, particularly with the high-strength geotextiles and reinforcement applications. He's currently serving as a technical director of TenCate Geosynthetics group in Asia. And I can proudly say that he's a proud Aussie. He got his engineering degree from University of New South Wales, very early stages. He already worked in this particular field for more than 40 years, covering Australia, Europe, North America, and Asia region. And during this period, he also was part of a number of international organizations developing standards and code of practices. Now, Chris also acted as a technical advisor on many large geosynthetics projects in field of embankments, reinforced soil techniques, coastal, hydraulic, and environmental. So you have a plethora of experience and vast knowledge of using geosynthetic materials in different applications. As well as he also co-author as well as author of over 50 technical papers, and he presented these papers in different conferences and seminars throughout the world. I won't take any much time. Please join me in welcoming Chris to present his talk today. Thanks, Chris.
Okay, thanks Rajesh for that introduction. The subject of these webinars are basal reinforced embankments, and because that is quite a large subject area, what I've done is to split them into 2 parts. And part 1 is what we'll be covering today, and that's basal reinforced embankments on soft foundations. The second part, which I'll come to shortly, we'll cover on the webinar next week. Now, just a general introduction to basal reinforced embankment applications. And what I'm going to do, refer to here, and I'll refer to quite a bit throughout the talk, is to a code of practice called BS 8006. And if you're not familiar with that, it's a British standard code of practice on reinforced soils. And one of its chapters actually deals with basal reinforced embankments. So a lot of what I referenced today, I'll be referenced into BS 8006. So in these 2 webinars, today and the one next week, We're going to follow the BS8006 approach to design of basal reinforced embankments. And what BS8006 has, it has three types of embankment applications. This first type in the diagram at the top is where we have the basal reinforced embankment on a soft foundation. And you can see the photograph there on the top right, where the basal reinforcement has been laid out on the soft foundation, and they're starting to place embankment fill on top to construct the embankment. The second type of application covered in BS8006 is basal reinforced piled embankments, where piles or columns are inserted into the soft foundation. Again, the basal reinforcement on top and the embankment built on top of that. And you can see an example there in the bottom right photograph. There you can see the pile caps at the surface, the basal reinforcement, and then starting to place the embankment fill. And then there is a third application, basal reinforced embankments which span across voids. And this is the third application covered in BS8006. But today, we're just going to do part one. And so we're just going to spend our time on this first application only, where we have the basal reinforcement underneath the embankment, and that sits on top of a soft foundation. The other two applications we'll be covering next week. Now, some fundamental concepts about basal reinforced embankments on soft foundations. So to understand these, I think is quite important. And what we do is we place a layer of reinforcement at the base of the embankment on top of the soft foundation. And when this layer of reinforcement intersects a potential failure surface that passes through the embankment, what we're expecting from this basal reinforcement is for it to provide additional shear resistance at the base of the embankment. And if you have a look in this magnified section here, we have the potential failure surface. This is the basal reinforcement here. And then at the point of the potential failure surface, tensile loads are actually generated in the reinforcement due to the outer balance forces that are acting. And then as these tensile loads get further away from the potential failure surface, these loads are then redistributed into the adjacent soil by the action of bond resistance. So that when we come to calculate and analyze this problem, we calculate the reinforcement loads, but also we calculate the bond resistance as well. Normally, we don't think about the bond resistance so much because it's common for the tensile loads here to actually predominate. So most people talk a lot more about this. Now, the point about this fundamental concept is that theoretically, all soils can be reinforced. But what naturally happens is the poorer soils, for example, the soft and softer foundation soils, as they get worse, they require more reinforcement to achieve the same level of improvement. But the thing to remember is that you can reinforce all soil types. So what are the problems with the construction of embankments on soft foundations? Well, two types of problems arise. You have problems of instability and problems of settlement. An example of the instability problem here is shown in a photograph in the bottom left here. And this instability can occur if the soft foundation has inadequate shear strength to support the embankment loading, such as shown in the top right diagram here. This instability is really a function of the embankment weight and the geometry of the embankment. And it's also a function of the rate of application of the load. For example, if you apply the embankment load too quickly, you can shear the soft foundation. Whereas if you apply the load a lot more slower, you won't shear the soft foundation. The second type of problem is settlements. And these occur due to the consolidation of the soft compressible foundation. And what's particularly the problem is when these settlements occur over a relatively short distance. For example, what's shown in the middle photograph here at the bottom. You can see the settlement here is occurring at a short distance, and this can create trafficking problems. Whereas if the settlement was nice and uniform over a long length, you probably wouldn't notice the difference. And the key point about these settlements is it's not just the magnitude of the settlements that can be a problem, it's also how quickly or the rate of the settlements that's also important, as shown here in this bottom right diagram. And basically the amount of settlement is really, again, it's a function of the embankment weight, and it's a function of the foundation soil geometry, as well as the level of compressibility. So these are the details we'll be looking at today. So what are the solutions we can apply to enhance stability and consolidation of soft foundations? Well, let's first of all look at a couple of solutions for enhancing stability. And these are the diagrams shown in the middle part of the slide here, the stability solutions. We can construct embankments by stage construction, where we place the geosynthetic separator in this case, and we build up layers of the embankment fill to certain heights, and we let that settle and consolidate, and then later we come back and build up the next lift, and we can repeat the process until we've constructed the embankment. This used to be a practice many years ago. It was common, but today it's not really used today because of the time it can take to build up these embankments to the design height. And these days, other solutions are applied. The second way of enhancing stability is we can construct berms onto the sides of the embankment to aid in the stability of the embankment. The problem with this type of technique can be that we may involve high land acquisition costs, because instead of acquiring land for this width of embankment, we're having to acquire land for this width of embankment. Now, the third solution is we can use geosynthetic reinforcement at the base of the embankment and construct the embankment on top of that. And this solution is a good all-round solution because we're using the geosynthetic reinforcement to be able to maximize the steepness of the side slopes of the embankment and also maximize the height that we can build the embankment to while keeping the whole structure stable. And so this can actually help for stability purposes. When it comes to controlling settlements, there are, again, a number of solutions available to us. Normally, we can provide surcharge on the top of the embankment to aid the rate of settlement of the compressible foundation. And of course, later we strip the surcharge off and build the embankment pavements. To accelerate the rate of consolidation of the soft foundation, we may apply vertical drains, or in Australia, you refer to them as wick drains, into the soft foundation soil to accelerate the consolidation. And again, we also can apply surcharge to make this work even quicker. And the third case is we can introduce piles or columns into the soft foundation, again with the geosynthetic reinforcement and embankment. And the role of the piles or the columns is to prevent the settlement and consolidation from occurring, so we can just build the embankment directly on top of the pile caps and the columns. Now here in each of these cases, number of these cases, you'll see that geosynthetic reinforcement applies. So we can use geosynthetic reinforcement just for stability purposes. We can use geosynthetic reinforcement when we want to surcharge. We can use geosynthetic reinforcement when we use wick drains. And we can use geosynthetic reinforcement when we use piles or columns. Now, in today's talk, we'll be covering the cases here at the bottom left and of the two cases in the top right. The case in the bottom right we'll be referring to in next week's talk. So as far as the mechanics of basal reinforced embankments on soft foundations are concerned, I think one way of looking at it is to look at it in a fairly simple way. And a simple way would be, say, we can look at it in terms of bearing capacity theory, where we have the case of the unreinforced embankment, which is shown here on the left-hand side of this diagram, and then the case of the reinforced embankment, which is shown on the right hand. And let's look at what the benefits are or the differences are in terms of simple bearing capacity theory. Now, taking the unreinforced embankment first, what we have in an unreinforced embankment is we have vertical loading from the weight of the embankment fill. And then on these shoulders of the embankment, we also have horizontal outward shear stresses acting. So these vertical loading and horizontal shear stresses act on the surface of the soft foundation under the side slopes of the embankment. And this, of course, is a similar case to, say, a rough surface footing subject to vertical loading and outward shear stresses. And if we look at that in terms of bearing capacity theory, what we have is, and we'll look at it in terms of this bearing capacity factor. If there's just vertical loading only, this factor, of course, is 5.14. But if we now also introduce to it this outward horizontal shear stress, the outward horizontal shear stress actually reduces this bearing capacity factor down below 5.14. This is for the unreinforced embankment case. Now let's turn to the reinforced embankment case. And what we have, again, we have the vertical loading of the embankment and the horizontal outward shear stresses. But now we're introducing a layer of reinforcement at the base of the embankment. And what this reinforcing layer does is it changes the outward horizontal shear stresses, it absorbs those, and it imparts inward horizontal shear stresses on the surface of the soft foundation. So in terms of bearing capacity, what we have is that we actually have effectively a rough footing subject to vertical loading plus inward stress, horizontal shear stress. And so when we come down to this diagram here, we're vertical loading only, which is the factor 5.14. And then because we have now inward horizontal shear stress, depending on the magnitude of this, then that bearing capacity factor can actually increase above 5.14. So for the unreinforced embankment, the bearing capacity factor drops below 5.14, and the reinforced bearing capacity embankment, the factor increases above 5.14. So this difference in effective bearing capacity are normally equated in practical terms is that basal reinforced embankments can be constructed higher than unreinforced embankments, or their side slopes can be constructed steeper than unreinforced embankments. And this is where the benefits and the advantages of basal reinforced embankments over unreinforced embankments are normally determined and calculated. Let's look at the development of tensile loads in the reinforcement of a basal reinforced embankment on a soft foundation. And for this, I'm going to take from BS 8006 document. Now, BS 8006 normally refers to this type of application as a short-term design strength problem. And the reason it calls it a short-term design strength problem is that the design strength of the reinforcement is only required for a time period that is less than the design life of the structure. So, for example, the design life of the embankment may be 100 or 120 years, but the design life that you want from your reinforcement is less than that. And I'll show you why that is here now. So here we have the embankment constructed on the soft foundation with the basal reinforcement. Then as we place the fill on top of the reinforcement to build the embankment, what happens to the tensile load in the reinforcement is, and that's this blue line down here, is as the embankment gets higher, then the tensile load in the reinforcement increases. And it reaches a maximum when you've constructed the embankment to the completed height. Then what happens is the soft foundation here consolidates under the weight of the embankment. And as it consolidates, it gains in shear strength. And as it gains in shear strength, it can support more of the weight of the embankment. So it doesn't need so much of the reinforcement anymore. So what you find is the load in the reinforcement starts to drop off with time. And it comes at a point out here where the soft foundation becomes fully consolidated. And at this point, the soft foundation can support the full loading of the embankment by itself. So it really doesn't need the reinforcement anymore because it can support the embankment. And so what you then find is that after this, then the load in the reinforcement remains constant with time. Now you might well ask, well, if the soft foundation is carrying all the weight of the embankment, why is there still a residual tensile load in the reinforcement? Well, the reason for that is that while this soft soil is consolidating, the embankment is actually deforming. And it deforms to a kind of shape, something like this, shown here on the right. And when it deforms to that shape, some residual tensile stresses in the reinforcement are locked in. And they remain in the reinforcement with time. The levels are normally fairly low, probably around a maximum of, say, 20% of the maximum load in the reinforcement. So they're relatively small, but there are some residual tensile stresses normally locked in. Now, from a design point of view, what we're interested in is we're interested to find out what's the maximum load in the reinforcement. And we're also interested to know is how long does it take for the soft foundation soil to consolidate and can support the full load of the embankment. So we're interested in this level, we're interested in TR, and we're interested in the consolidation time. And that's what we've come to determine as part of the reinforcement requirements for this embankment. And you'll notice, of course, is that we only need the reinforcement until such time as the soft foundation soil consolidates. And that may be 5, 10, 15 years, whereas the embankment itself is designed to last for 100 or 120 years. Now, BS 8006 sets out a number of different design limit states for basal reinforced embankments on soft foundation. In fact, it sets out 5 of them. They're shown here in diagram form. And what you have to do is work your way through each of these cases and find out what reinforcement strength and what embankment geometry you need to satisfy these cases. And then you take the worst case. So there's here the edge stability of the embankment shoulders need to be stable enough. You need to prevent against rotational stability in the embankment. You need to prevent lateral sliding across the surface of the reinforcement. You need to prevent the soft foundation soil from extruding out of the base. And then you need to control the strain also in the reinforcement. Now, the thing here, this rotational stability, this is normally the critical one when it comes to determining the load in the reinforcement, and it dominates. And if you look at this, the rotational stability is about approximately equal to the horizontal outward sliding component, which is effectively this component on top here, and the foundation extrusion component, which is this component down beneath. So normally it's the rotational stability that dominates the determination of the load required in the reinforcement for stability. Then this fifth case is actually a serviceability case, protecting deformation And here, this allowable strain in the reinforcement, so that this doesn't strain too much, and this can be important. And we'll look at this particular issue in a later slide. So we carry out these calculations to determine what the maximum load is in the reinforcement. Now, there's a number of methods we have available to us today to enable us to analyse and design embankments on soft foundation when it comes to determining the maximum tensile loads in that basal reinforcement. Generally, the solutions break down into three types of solutions. The first one here I've listed are plasticity solutions, and these are simple bearing capacity type solutions, which I spoke to briefly earlier, utilising bearing capacity theory. And you can see one set of, they come in a form of chart, and you can see one set of charts here. They're quite quick, approximate solutions for conventional cases. And again, these design charts, for example, here in this design chart, you can see the yellow zone is for the unreinforced case, and then the orange zone is for the reinforced case. And then you can quickly compare the two different cases for these charts. These plasticity solutions are pretty simple, they're simplistic, and they give conservative results. So for doing a quick design on the back of a beer coaster, for example, these sorts of charts are all pretty helpful as far as that and working out what an initial costing could be. The next type of method we have available are these limit equilibrium methods, which are really slip circle analyses. And of course, these days they're all run on computers, which make them all very easy. And in diagram form, this is effectively what's actually being worked out. You have the embankment with the basal reinforcement, and we use the computer to do the slip circle analysis. So we have slip circles through the embankments, and what we determine at each location along the base of the embankment, it works out the worst case for which what tensile load we need in the reinforcement to provide the required stability. So along the base of the embankment, what we can come to is what the tensile force we need in the reinforcement along the base of the embankment. And at some point here, at some location, it comes up to a maximum tensile force. And that's the answer which the computer spits out for a solution. Again, these are good solutions for conventional cases and are used a lot, and they're very convenient to use because they're all run by computer these days. Now, the third method are continuum methods. Of course, these are finite element and finite difference type techniques. Again, computer analysis. And these methods require quite sophisticated inputs. And sometimes, in fact, in a lot of cases, you don't have those sophisticated inputs. So it takes somebody with experience really to apply the inputs that this sort of computer analysis requires in order to come up with realistic responses. Now, an example of that is shown in the top right, where here there's a rather trapezoid, triangular, if you like, embankment here. And down in here, this is a soft foundation soil beneath. And here you can see the graphics from an unreinforced case. These are the horizontal shear strains in both this direction and in that direction, in the outward direction. And what this method showed, this program shows, is that, well, if you put a basal reinforcement in there now, then sure, the shear strains above the reinforcement don't change very much, but the shear strains in the soft foundation soil beneath the reinforcement are much reduced, and this gives the stability for this structure. So these continuum methods today give nice graphical outputs and enable you to easily visualize what the reinforcement is doing. Also, these methods, you can model quite complex geometries, conditions, and procedures. But again, I'll stress you need the experience to operate these and interpret them. So you have a choice of all three. And at the end of the day, what you're trying to work out is what is the maximum load in the reinforcement And how long does this load have to last for? So coming back to the slide that we saw before, where we have the maximum load in the reinforcement over the consolidation period of the soft foundation soil. And while in analysis, this may be really what's happening, the blue line, from a design point of view, we simplify that and assume that, okay, the maximum load remains constant with time up until the consolidation time, and then it drops off to naught. So we make a simplified assumption from a design point of view. Now let's come to the reinforcement strain. So we've looked at the maximum load. Let's now look at what needs to be the reinforcement strain. And again, I'm going to take it from BS8006. So to meet the serviceability requirements, we need to apply a maximum allowable reinforcement strain to control how much this embankment strains and deforms. For example, as we load up the embankment, then under the weight of the embankment, the soft foundation can deform, and you can get lateral spreading, deformed shape, and you can get vertical sinking of this embankment. And so what you need to apply to the reinforcement, this deflected shape, is that it can only strain so much and keep everything under control. And BS8006, for example, takes like this, and what it does is it applies a maximum strain of 5% to the reinforcement. And what assumes that if the strain in a reinforcement is less than or equal to 5%, then your embankment will remain in a serviceable condition. Now, it's important to understand how this is applied, how this 5% is applied. And so what you need to do is you need to go to these isochronous curves, creep curves for the reinforcement material. And so it's not a matter of just applying 5% strain to the initial load strain curve of the reinforcement, because what you're interested in is applying this 5% strain at the consolidation time. So this blue curve here. And so the change of the shape of the curves of the reinforcement can change with time, but it's this particular curve at the consolidation time, whether this can be at 5 years or 10 years or 15 years, that's important. And so we apply a maximum reinforcement strain of 5% at the consolidation time of the soft foundation. That gives us the load in the reinforcement, and then this factor is applied to be able to calculate what needs to be the initial strength of the reinforcement. So it's this we get from these isochronous creep curves at 5%, not the normal conventional type of load strain curves. Now I want to digress over in the next couple of slides and talk about basal reinforcements for embankments in particular. And the way I'm going to do that is talk in terms of the types of reinforcements that we have as a company, and explain this because the same sort of things applies to other sorts of reinforcement products from other companies. From our company, we've been involved in geosynthetic reinforcements for many years, going back into the 1970s, so some almost 50 years now. We've been involved in these materials. A lot of our reinforcement are actually based on high modulus polyester yarns. And one of the reasons we've concentrated on high modulus polyester yarns is that they are high strength, so you can make very strong materials. They have low, well-defined strains, and strains doesn't change very much over time. And they have excellent in-ground durability over long periods of time. And we have two families of basal reinforcements. One family is based on woven polyester geotextiles, and there's a photograph there of the particular products. And these use, of course, high modulus polyester yarns as the reinforcing component. You get high strengths that can hold strains for long periods of time. Very well-defined engineering properties. And of course, these products perform a good bond with the adjacent soil. They're made very high strength, so you can have them anything from 100 kilonewtons per meter in strength, anything up to say 2,000 kilonewtons per meter in strength if you require something so strong. The second type of reinforcement we have are geogrids. And again, these are made from high modulus polyester yarns as a reinforcing component. But you'll see these are black in color. And the reason they're black in color is that they have a coating of PVC on the outside of the polyester yarn. And that makes them look black in color. But again, we make them in high strength, again, controlled strains at long periods of time, well-defined engineering properties. And again, they also perform good bond with the adjacent soil. And we manufacture them in tensile strengths ranging from 40 kilonewtons per meter to 800 kilonewtons per meter. So there's a wide choice of these reinforcement products which can be provided. Now, it's not just the initial strengths that's important when it comes to soil reinforcement geosynthetics. And I want to explain this in a bit more detail in the next couple of slides. Now, when you've calculated the maximum load in the reinforcement of a basal reinforced embankment using your computer analysis, what effectively you've determined is you determine a geostatic reinforcement design strength, this red line here. And this design strength acts at the base of the embankment over a required design life, which of course is the time it takes for the soft foundation soil to consolidate. So over this period. But in calculating the design strength, we then need to work out, well, what does the initial tensile strength of the reinforcement have to be if this is what the long-term design strength has to be? And the way we go about this is a pretty standard protocol and procedure these days, where we apply factors to this design strength to enable us to work our way back up through here to time t equals 0 to tell us what the ultimate strength of this reinforcement needs to be. Now, BS8006 approach, it has quite a detailed procedure which accounts for different parameters, and it uses reduction factors. And this is over here in the top right, the equation that's in BS8006. So what it is TD, this is the design strength, which we've analysed and calculated. And this is what the characteristic strength is, the initial strength. And then you apply these reduction factors to it. So you have a reduction factor for weathering, one for installation damage, choice of 2 for creep, and then 1 for environmental effects. And this enables you to calculate or move between the characteristic strength, initial, and the long-term design strength. Different factors apply to this equation. And so you can see it, I've shown here in graphical terms here. And the main movements are really is a reduction factor due to loss of strength due to installation damage effects. And this is when you compact rock and fill against the reinforcement, it can lose some strength. This next one is if you apply a constant load to the reinforcement, it can lead to a reduction in strength due to creep. And then the second one here is a durability effect where the reinforcement can be buried in the soil, and over time it also may have an effect on the reinforcement. So it's these three areas, installation damage, creep, and environmental effects, which can have a significant effect on how the reinforcement behaves with time. The thing to remember, of course, I think here down the bottom left, is for short-term reinforcement application, such as an embankment on soft foundation, then the time period, the design life here, may only be relatively short until the soft foundation is consolidated. So it could be 5, 10 years. But if, say, you had a long-term reinforcement application, for example, like a retaining wall or a reinforced slope, then the reinforcement design life may be a lot longer, up to 100, 120 years. Okay, so let's look at these three major factors in a little more detail. Now, I'll contain my talk here to just high modulus polyester reinforcements. It's the area I'm most familiar with. And I'm going to talk about the effect of installation damage, look at the effect of creep, and we'll look at the effect of this in-ground durability. So let's turn first to installation damage. And this, of course, is where we're compacting aggregates and granular material adjacent to the reinforcement. And what we find is that depending on the type of polyester reinforcement we have, depends on how much damage you can actually do to it. And for example, this diagram down in the bottom left, this is an installation damage reduction factor. So as the factor gets bigger, we're doing more damage to the reinforcement versus the size of stone that we're compacting against the reinforcement. And what you can see here is that the polyester woven geotextiles, they're the ones most prone to installation damage. And that's the green area here. And the reason they're most prone is that you have these polyester yarns are completely exposed to the aggregate you're compacting against it. So you can do more damage here, okay? Polyester geogrids, of course, have a PVC coating, and this coating does help to protect the polyester yarns. And so while you can have some damage, it's not as much as, say, woven polyester. And then you can have polyester composite materials, which are manufactured in such a way is that you have no installation damage done to these particular materials. So you have total installation damage resistance. So it depends, but also look here, the amount of damage done also depends on the size of the stone. So as the size of the stone gets bigger, you can do more damage to it. And so this is why for a lot of reinforced source structures, it's a good idea to try and limit the maximum size of the type of fill that you're using against the reinforcement. Some cases where this is impossible to do and you're having to work with large size aggregate fills, for example, greater than or equal to 150 millimeters in size, then maybe you require some specific testing to work out what is the actual reduction factor you should use as part of the design calculation for your basal reinforcement. The second type of behavior, this is to creep. This is where load is applied, tensile load is applied to the reinforcement over time. For high modulus polyester reinforcement, there's very good resistance to creep effects. And what you can see from this set of curves down below here, where I've plotted the initial tensile strength of the reinforcement versus strain. And this is at different times, different design lives. And you can see at time t equals 0, which is a typical sort of tensile test. You get the blue line here. And then the green lines are, say, at 10 years, at 60 years, at 120 years. Now, there are two ways of looking at this chart. You can look at it in terms of load only. So in this way, we look at it coming down this way and horizontal. So we may start off at time t equals 0, 100%. Then at 10 years, the tensile strength of the material left is somewhere just under 70% at 10 years. But you can see all the change has occurred really in the first 10 years. After 10 years, very little change in the strength occurs, even up to 120 years. Now, if you look at it across this way, across this chart in terms of strain, you'll see the same thing happening. In that initially, there's some strain, increase in strain from t equals 0 to 10 years, this here. But after 10 years, there's very little change in strain in this type of reinforcement, even up to 120 years. And normally, The typical loads in the reinforcement are normally around about 40% of the tensile strength of the material. And so at the 40% level down here, you can come across here and you can see the change in strain at 40% load is normally, it's less than equal to 1% over 120 years. So it's very little increase in strain over long design lives. And for those of you who've worked on New South Wales and Queensland Highway Department specifications for reinforced source structures, you'll see one of their requirements is that the creep strain in the reinforcement has to be less than 1% over 120 years. And this is where it comes from. And so for high modulus polyester, if it's loaded up to about 40% of its ultimate, it'll meet that requirement. Now, the third factor here is in-ground durability. And high modulus polyester reinforcements are very stable when placed in normally in-ground conditions. Very little change in strength over periods of time. You can see in the table below, the reduction factor at 20 degrees C, which is normal ambient soil temperature. Less than 10 years, no change. 50 to 60 years, 2% change. 100 years, 4% change. And 120 years, 5% change. So very little change in time, and these materials are very durable. Now, what we've done so far in the analysis of these basal reinforced embankments is we've analysed the load carried in the basal reinforcement in this direction, across the width of the embankment. And this is the design strength, TD, across the width. Now, there's also loads in the reinforcement in the longitudinal direction, but these types of loads are fairly minimal. And they're normally only about 20 to 50 kilonewtons per metre. And their magnitude is really determined based on how the contractor places his fill on top of the reinforcement. If he places it in a good manner, then these loads generated in the reinforcement in the longitudinal direction remain quite low like this. Whereas the loads in the cross direction can normally be 10 times these, so 200 to 500 kilonewtons per metre in the cross direction. So practically what should be done on site is to cater for this is to use a unidirectional reinforcement material. And this reinforcement material should be placed across the width of the embankment in one continuous sheet with no joints. And then adjacent pieces can either be overlapped or with seams sewn because this is where minimal tensile loads occur in this direction. Now let's look at the next couple of slides at using what I refer to as prefabricated vertical drains, or PVDs. And of course, in Australia and New Zealand, there you refer to them as wick drains, but it's the same thing. So let's look at this technique to accelerate the rate of foundation consolidation. So without wick drains, we have this particular case shown in the upper right, where the embankment loading plus surcharge drives the pore water out of the soft foundation and drains across at the surface. And consolidation time here in this case can take many years, with 10 years not uncommon. And of course, over this 10-year period, some of these embankments may require extensive maintenance. If you're dealing with wick drains, then you install the wick drains into the soft foundation soil. So now these excess pore pressures just drain to adjacent wick drains and then drain quickly out through the surface. And so the rate of consolidation in the soft foundation is much quicker. And it may only take 6 to 2 years in general for the soft foundation soil to consolidate, depending on how closely spaced these wick drains are. Normally what's done practically is you design the wick drain layout to achieve most of the consolidation during the construction period of the embankment project. And normally, practically, you normally find that these wick drain spacings, in this case, are normally between 1 to 3 metres in spacing, what you find. Now, there are a variety of different wick drain types available. The most common has a geotextile filter, as you can see here, with an extruded rib polymer core inside it. The width of the wick drain is normally about 100 millimeters, and the thickness is 3 to 5 millimeters in thickness. These wick drains are only required to transport small volumes of water under varying confining pressures, and the drainage function of these wick drains really has to be maintained under vertical deformations, embankment settlements and things like this. And that's why the actual core structure of the wick drain is quite important, that even if the wick drain bends and there's some buckling occurring, the pore water can still make it out through the wick drain. Now, the wick drains are actually installed inside a hollow steel mandrel, such as shown here in the bottom right photograph. You can see the wick drain coming out at the bottom. These mandrels are vibrated into the soft foundation layer to the base, and then the mandrels are withdrawn back out to the surface, and the wick drain remains in place in the soft clay foundation layer. Normally, the installation rates can be quite very high with PVD installations. In an ideal world, each machine might install something like 1,500 meters per hour, which is a lot of wick drain, but more in this effectively in ideal conditions. But in a lot of cases, you don't have ideal conditions. And so actual installation rates may end up being less than this. Normally what's done, depending on how many wick drains and how quickly you need to install them, you just bring more equipment on site, so you have as much equipment as you need to install the wick drains in the required period of time. Now, when you use wick drains in conjunction with basal reinforcement, the load profile in the basal reinforcement follows generally what occurs if no wick drains are used. So, for example, we've seen this chart before. We have the upper blue line. As you build up the embankment, this load in the basal reinforcement increases with time. It reaches a maximum when the embankment is completed, and then over time the load drops off in the basal reinforcement as the soft foundation soil consolidates. When we use wick drains, the same thing occurs, but slightly different magnitudes. As we build the embankment with the wick drain, the loads in the reinforcement increase, and they reach a maximum when the embankment is completed. But you'll see that the load in the reinforcement now is not the same as what it was if we have no wick drains. Now, the reason for that is that even during the time we're building the embankment, is that this soft foundation soil is already consolidating with the wick drains and gaining in some strength. And so therefore the load in the reinforcement never reaches the same level as if the case we don't have any wick drains. And then after we've finished the embankment, the load drops off in the basal reinforcement, and it drops off much quicker because the PVDs are accelerating the rate of consolidation of the soft soil. So the time over which we need the reinforcement is shorter than compared to, say, when no wick drains are used. And again, as I've said already, this consolidation time may be anything from 6 months to 2 years, depending on how we've designed the wick drain layout. Now, coming to design the reinforcement, again, we take the same approach as we do if we have no wick drains being used, but the design life is less, and the load in the reinforcement is less than if we have no wick drains. Now, when it comes to building these embankments with PVDs, normally what should be avoided is we shouldn't be driving the PVDs through the geosynthetic reinforcement. Because when we do that, we just put holes in the reinforcement and it reduces its strength. And so the best practice is normally to construct what we call upside down construction. And what that is that we place a geotextile separator on the soft foundation. And on top of the geotextile separator, we place and build a drainage blanket. Now, this drainage blanket also doubles as a working platform so that the PVD rigs can traverse across the surface. Then we install the PVDs down through the geotextile separator into the soft foundation. After we've done that, we place the basal reinforcement across the top of the drainage blanket. And then finally, we build the embankment fill on top. You can see in the top photograph here where the drainage blanket is made from sand, and that's normally the most common. And here you can see the PVD rigs installing the PVDs through the sand drainage blanket. But some cases you'll find that you can't obtain sand, whether environmentally you're not allowed to use it, or it can be very difficult to obtain, very expensive. And normally what can happen then is that normally you can crush gravels, use crushed gravels as the drainage blanket, as you can see in the bottom photograph here. You can see the geotextile separator underneath the gravel drainage blanket. And here they're installing the wick drains down through the gravel drainage blanket layer. Then placing the basal reinforcement across the top of the drainage layer. You can see in the bottom left photograph here, and then the embankment fill placed on top, plus any surcharge if you're surcharging it. Now, I want to give you a brief case study, an example of this type of technique, and I've taken this one from Australia. And it's the part of the Pacific Freeway, right in the north of New South Wales, near the Queensland border. Here on a map of Australia, you can see the orange dot here. This is the location right near the Queensland border. And of course, it's part of the Pacific Freeway linking Sydney to Brisbane. This contract was a design, build, maintain contract for 10 years. So the contractor had maintained the highway, this highway section for 10 years. So what was important to him, of course, was that anything he could do during the construction phase that would prevent him having to come back and do later maintenance, he would go for that. The length of this particular project is about 30 kilometres in length, and it's a standard cut and fill type operation. Now, the bottom photograph you can see here, this is the coast on the right here. Just up above the photograph is actually the Queensland border. And you can see the existing Pacific Highway coming down through here and running out towards the southwest. And this is the new freeway section, which starts here and runs south down here, much closer to the coastline. Now, this freeway section traverses a series of old submerged river valleys with soft soil deposits. And these soft soil deposits varied anything from 5 metres to 15 metres in depth. And the water table was quite close to the surface. It was in about 1 metre. So you can see the sort of vegetation at the surface. So it's a vegetated crust at the surface. You can see the water table quite close to the surface here. Below the water table, very soft silty clay, undrained shear strength, probably less than 10 kPa, and then increasing linear with depth until at some depth down here, maybe below hit a firm foundation where the undrained shear strength increased. A number of things about this soft silty clay layer is the depth of this soft silty clay layer could change very quickly from over short lengths. And this created some problems with how to design these embankments in this highway structure. Now, these embankments, they had to be constructed quickly to enable a maximum time for settlement during construction period, and basal reinforcement plus wick drains were used here. So here's a typical section through the embankments. And again, these embankment heights were from 2 to 5 meters in height. The crest was about 30 meters in length, a dual carriageway freeway, and 1 to 2 side slopes. Now, to meet the performance requirements of stability and consolidation, the way these were designed was a separation geotextile was placed on the soft foundation. Then there was a 0.5 meter bridging layer placed of pretty low quality fill. And then on top of that, a 200 millimeter thick drainage blanket was placed of crushed gravel. And that crushed gravel was quite an expensive item, and it had to be won from cuttings further along the freeway length and crushed, so it's quite expensive. So they only put that in 2 meter thick lifts. Then the PVDs were installed to the full depth of the soft foundation at spacings from 1 to 3 meters. And then on top of this, the basal reinforcement was placed. And again, depending on how the depth of this soft layer, how soft it was, and the height of the embankment, the strength of the reinforcement ranged from, say, 200 kilonewtons up to 800 kilonewtons were actually placed. And then after that, the embankment fill was placed, and this was variable size material. Again, one from cut sections along the freeway. A surcharge of 1 meter was placed on top of the embankment, which allowed an accelerated rate of consolidation, and this was stripped off after 12 months to allow the pavements to be actually built. So here we can see, in this case, the drainage blanket, and you'll see it's a crushed gravel coming from a cutting further up along the length of the freeway, with the PVDs installed through and down into the soft foundation. And again, only about 200 millimeters of this material was used to save on its use. And the PVDs were spaced 1 to 3 meters on a square grid. So once the PVDs had been in place and the drainage blankets here, you can see the basal reinforcement being placed across the top of the drainage blanket. And then on top of the reinforcement was placed the embankment fill. And you can see the type of fill here. It's quite random fill with quite large granular particles in this, which had come from cutting further up the road. And again, it just gone through some primary crushing before it was placed and spread over the reinforcement. And so there was a high level of installation damage that will be done to this reinforcement. For example, you had granular drainage blanket beneath with random fill placed and compacted on top. And so on site, what was done was a series of on-site installation damage tests were done with these fills and the different reinforcements to find out the safe reduction factor for installation damage that should be used in the design calculation for this basal reinforcement. These are construction of the embankments. You can see here, it was a standard earth moving type procedure using scrapers and bulldozers to place the embankment fill, and then a compaction of the embankment fills, as you can see here. In the area where the PVDs and then the surcharge, what you can see here in this case, you can see all this water lying on the side of the embankment. This is not rainwater or anything like this. It's actually pour water coming out from the blanket drains at the sides of the embankment and draining away from the embankment. Here, it's always very good practice to ensure that the pour water can actually physically easily drain away from the sides of the embankment, and you don't want it to dam up against the edges of the embankment because that can give you problems. Okay, so after a year, the surcharge was stripped off and the pavements were constructed. So here's the freeway section completed with the pavement layers constructed. Here, you can see the embankments are quite low. It fits in well with the low-lying areas, so there's not a lot of trying to minimize the amount of embankment loading. The pavement layers were designed according to New South Wales main road freeway standards, and depending on different lengths along this freeway section, both rigid and flexible pavements were used. So some concluding remarks. I think the first thing I want to say is that the design and analysis of basal reinforced embankments on soft foundations, it's a well-recognised and proven technique. The basal geosynthetic reinforcement provides short-term stability until the soft foundation can fully support the embankment loading. And in this particular case, the major tensile load in the basal reinforcement occurs in the direction across the width of the embankment. Basal geosynthetic reinforcement enables embankments to be constructed higher and have steeper side slopes than would be the case without using reinforcement. Now, wick drains may be applied in addition to basal reinforcement to accelerate the soft foundation consolidation. And the way this is designed and planned is to have the majority of the foundation settlements to occur within the construction timeframe, so that once the construction timeframe is completed, then the contractor doesn't have to come back later and carry out quite costly maintenance, which may occur during subsequent years. Okay, so that's the end of my talk. Thank you for your attention.
Thanks, Chris. It's a fantastic presentation, I should say, with a great insight on using high-strength geotextile in designing the reinforced embankment. I have some good questions already come for you. So first question.
Very, very easy ones, I hope.
Yeah, Chris, I think so. There is nothing hard for you. I can say that. So it's everything is easy for you. The first question is, Chris, do geogrids need to apply with a separator geotextile, or arching effect can be relied upon?
I think generally for embankments on soft soils, you don't need a separator with a geogrid. You just use the geogrid by itself, except where the surface of the soft ground, if you're applying it directly to the surface of soft ground, is very soft. In that case, if it's very soft, you probably are going to need a separator beneath the geogrid to prevent any soft mud from coming up through the geogrid. But generally, if you've got a good vegetation crust on the surface, slightly over-consolidated surface, then if you're thinking of using a geogrid there, you probably don't need to use a separator as well as the geogrid.
Thanks, Chris. Another question is, can you comment on how cutting the woven PET affects the long-term tensile strength, and what is the best practice to cut?
Sorry, could you repeat that again?
Sure. Can you comment on how cutting the woven PET affects the long-term tensile strength, and what is the best practice?
Okay. If you cut the woven polyester or any reinforcement, the strength goes to zero because you've cut it. It's no longer there. And so what you should avoid is trying to have to cut the reinforcement. And likewise, when I said for the use of wick drains, you shouldn't try and drive wick drains through the reinforcement, because you place holes in the reinforcement and the reinforcement just loses strength because of those holes are there. So you should avoid from doing that. And one of the ways of doing that, of course, is that upside down construction where the reinforcement goes above the PVDs. But if you're having to cut the reinforcement, then where you cut it, you don't get any strength transfer at all with the reinforcement. So you've got to either assume that and know that, or maybe you can lay out the reinforcement so that there's some sort of redundancy in the reinforcement that gets you over that problem. For example, you may put some reinforcement at different angles on the ground to be able to transfer the loans around where you've actually cut it. But it depends on what your application and what you're doing, really. But if you just cut the reinforcement, then there's no strength transfer.
Thank you, Chris. I think the question is keep coming. The other question is, Chris, in which situation would a geogrid be preferred over a woven geotextile as a basal reinforcement?
For basal reinforced embankments on soft foundations, you could use either if you wanted to. However, having said that, probably over 90% of the basal reinforced embankments built, especially those on soft foundations, use woven polyester geotextiles, and probably less than 10% use geogrids. Technically, there's no advantage over one versus the other for basal reinforced embankments on soft foundations. Probably what you'll find is that the woven geotextiles end up being cheaper than geogrids, especially when you're requiring strengths of 200 to 400 or 500 kilonewtons per metre. And that's normally why the vast majority of basal reinforcement being used is woven polyester.
Thanks, Chris. Now, next question is in a two parts. I will read the first part, and then once you answer it, I will give you the second part. Does the design grid and layers of basal reinforcement need to be kept sandwiched within the selected granular / frictional layers of fill to get the base effect of the reinforcement under the load of embankment?
Generally, for this sort of application, that's not a limiting factor. What you find is that these basal reinforcement, whether it's woven polyester or geogrid, develops a very good bond resistant with any adjacent materials. So, for example, even if you have a sandy material, which may only have a friction angle of maybe 30 degrees, it can generate its full tensile resistance in probably 1 to 2 metre distance. So very short bond length distance. So the necessity for having highly granular materials in conjunction with the basal reinforcement to develop that bond resistance is really not the particular case here. Other sort of applications, which we're going to probably talk about next week, there are advantages in having highly granular materials adjacent to the basal reinforcement. But for this case, for embankments on soft soils, that's never an issue.
Thanks, Chris. And the second part of that question is, would you mind commenting on the details of the thickness and engineering quality of the granular layer above and below the basal reinforcement? I guess you already answered it, but if you wish to add any.
Yeah, some cases, let me just say some cases. You see some basal reinforced embankments on soft foundations, they don't have PVDs, but what they do have is they have the basal reinforcement placed on the soft foundation, and then they place a granular material on top of the basal reinforcement to help drain out any excess pull or pressure out of the soft foundation. That's a pretty slow situation because you're having to wait for the pore pressure to come to the surface and then drain out. But people do put granular material on top of the basal reinforcement, in some cases, so that it does act as a drain above the basal reinforcement. But there it only has to be, even just a fairly clean sand can act as the drainage layer in that particular case.
Thanks, Chris. The next question is it correct that to meet the serviceability limit of 5% strain, the design tensile strength of the geotextiles is also limited to 5% strain plus reduction factors? Attendee is mentioning that he noted that the geotextile strength is much smaller at lower strength.
Yeah. What happens is when you come to do those calculations, you do the calculation for the ultimate limit state, which is the maximum load. And then from that, you calculate what the initial strength of the reinforcement should be. Then you do a second calculation for serviceability state. So you do two sets of calculations. So the second calculation for serviceability deals with the 5% strain limit. And at the 5% strain limit over the consolidation period for the soft foundation, you'll arrive at a required strength in the reinforcement also to meet that 5% strain. And from that, you apply again the sets of reduction factors again. And then you'll calculate what the ultimate strength of the reinforcement needs to be to satisfy that 5% strain limit. So you've now done two calculations. You've done one calculation to satisfy the ultimate limit state, and you've done a calculation to satisfy the serviceability limit state. And what you do is you take the worst case. So for example, at the ultimate limit state calculation, I don't know, I'll just use a number here. You may decide, work out that you need something 400 kilonewtons per meter in strength. When you've done your serviceability calculation at 5% strain, you may calculate that you need a reinforcement, say, 500 kilonewtons per meter in length in strength. And so what you do is you take the worst case to satisfy both, and that, of course, is the 500 kilonewtons per meter product. So you do two-step calculations and then take the worst case.
Thanks, Chris. Very comprehensive. The next question is, are there any specific drainage design consideration for use of basal reinforcement?
No, there's not. I mean, these basal reinforcement materials don't lose strength when there's water around or anything like this. So the strength and the behaviour of them is exactly the same in the dry as it is in the wet. So you don't have to take any precautions or make any changes for that. I think the thing for the drainage detailing is more to do with the drainage layer itself and the edge detailing of that drainage layer to ensure that the excess pour water can actually get out laterally through the drainage layer and out through the sides of the embankment and drain away.
Thanks, Chris. I think the next question is also repetitive with the first one for like a preference or preferred option of using woven geotextile with the biaxial geogrid. But this is actually adding how to decide the type of the basal reinforcement in between those two major types are preferred or selected.
Sorry, could you repeat that again?
Sure. Sorry, Chris. So the question is, which type of basal reinforcement is preferred one? Is it a woven geotextile or geogrids? I think so you already answered that at the start, but he said how to decide the type of the basal reinforcement in between those two major types are preferred or said, which one is selected? What are the bases on selecting that particular types, geogrids or geotextile?
Yeah, for basal reinforced embankments, what you calculate in the design, you could use either woven geotextile or geogrid depending on it met the requirements that your design calculation. So it's not dependent on the type of reinforcement other than when you apply these reduction factors to come up with the initial strength. So when you do the initial analysis and calculation, you come up with a design strength for the reinforcement over the period of consolidation. To arrive, and that is a general requirement, and it doesn't matter whether you're using a woven polyester or you're using a geogrid. In that case, but it has to meet that design requirement, design strength. However, when it comes then to working your way back to what does the initial strength have to be at time t equals dot, it then becomes very product specific because you're having to use these reduction factors for a particular product under consideration to come up with the initial ultimate strength of the material. And for example, woven polyester has different reduction factors, say, than geogrids. And so if you want to consider geogrids, you have to use the reduction factors for geogrids. And if you want to use woven polyester, you have to use the reduction factors for polyester. And then you'll work your way back to initial ultimate strength for either material. And they're probably going to be different strengths because they're different materials and different reduction factors, and then go from there. So once you start applying those reduction factors, you're working with very specific reinforcement type.
Thanks, Chris. Next question is it meaningful to clear vegetation covering soft clay or swamp, or just leave it in as the form of reinforcement?
I've been involved in this job for 40 years, and I've been asked that question for 40 years. A lot of engineers, especially the older ones, like to clear the vegetation, and they like to remove it all until they just get down to the dirt, if you like. Some case that can cause a lot of problems, because if it's soft and you start removing the vegetation, then you can be mixing up the soil and everything, and as you mix it up and work it, the soil gets softer and it gets worse, and it gets harder to then build on and place the geotextile. All those sorts of things can be a problem. And so what I always say is, if you have low-lying vegetation, the best thing probably is to leave that in place and try not to disturb it and try not to work it, and build whatever you need to do over the top. However, if you have small trees and all those sorts of things, you can't leave those in place. So this sort of tall vegetation, like tall trees and stuff, then you do have to remove that and get that out of the way. Anything like sort of some long grass or vegetation like that, my own personal experience, it's always better to leave that in place and just build over the top of it, because the soft ground is then is undisturbed when you fill on top of it. And also you have the benefit of the root matter in the grass and vegetation, which helps bind that soil together and gives you a bit of extra strength up your sleeve to work on.
Thank you, Chris. This is the last question. Why would the New South Wales and Weeks spec limit the strain at 40% strain at 1%? Sorry, I think so that's a bit confusing question. Why would the New South Wales and Weeks spec limit the strain at 40% strain at 1%? I think so I can answer that one. So if you go to New South Wales, R67, I think so, which gives some sort of understanding what you design with. At the same time, the other document is TMRS 100, which also gives you a good understanding on how to specify the high strain geotextile. But I will leave for Chris to add some more comments on that one.
Yeah. I think so where that 1% at 120 years requirement came from for creep strain in the New South Wales main roads and in Queensland main roads, you have to go back in history, and by history I mean back in the early 1990s. Probably a lot of you were babies back then, but I was still working. And what happened back then is many different types of reinforcements arose, and especially New South Wales main roads found it a bit difficult to determine what should be okay and what should not be okay. Now, some of these reinforcements were quite prone to creep, and for example, polypropylene type reinforcements, and their strain over 120 years is quite higher than 1%. And that was observed to be not a good thing for basal reinforced embankments, and that was probably the right decision. And so what happened back then is they put this creep limit of 1% over 120 years on the reinforcement, and effectively what that did is it basically threw out all polypropylene reinforcements and allowed polyester reinforcements. Which, okay, you could argue why they did it in that way and things like this, but it was probably right decision. And that's what's still there today. Things have moved on further than that now. I mean, if you go through the procedures of BS 8006 and that, you know, serviceability, the strain at 5% at the consolidation time, and even for things like slopes and walls at 100 per year, BS 8006 handles that strain limit in a much more rational way today, rather than just saying it needs to be less than 1% at 120 years. So times have kind of moved on past that original New South Wales and Queensland statement, although that statement probably still does apply. You know, it's okay. It's a bit conservative, but it's okay.
Thanks, Chris. I think that was the last question, and we covered on each and every question, Chris. So there is nothing left behind. All the questions are answered live to all the attendees. So
I killed everybody, you know.
No, thanks, Chris. As I explained it to you, yeah, there is no question which you won't answer or you can't answer, I should say. So thanks. Thanks, everyone. Thanks for your time. Thanks for your valuable time, I should say, nearly 1.5 hours for these presentations. And I hope you also thoroughly enjoyed Chris's presentation as well as his expertise. And thank you, Chris, no doubt about it. On behalf of all the attendees and Geofabrics, I would like to thank you for sharing your expertise and knowledge with us. And can't wait to attend our next session on next Wednesday.
Okay, thanks, Rajesh, and thank you all, everybody, for attending. Much appreciated. Thank you.
Thanks all.